quantum systems. Okay, so that our topic, let me put it here, is Floquet engineering quantum systems. All right, so before we start talking about what is Floquet engineering, before defining that, let me just tell you how these lectures are going to work. So we are going to have 5 lectures. So each lecture is 1.5 hours long. And additionally to the lectures, there is a homework set. So there's a homework set. So 4 to 6 questions, pretty standard homework set, like in any course. And this homework set will be available online. It's not there yet. I will upload it during the afternoon. So you can find the homework set at this website. It's sites.google.com/IFSC-USP BR. So this is my website, my web page, and you're going, if you go to that web page, you're going to find a link, and this link will have information about this mini course, in particular, a homework set. And we will have the opportunity to discuss this homework set tomorrow afternoon. So we have 1 hour tomorrow afternoon to discuss homework or questions in general. And the idea during these lectures and the idea for this homework is to make as informal as possible. So tomorrow we are going to come here and discuss these questions, this homework set, just have a collective discussion. And during the lectures, please interrupt me as much as you can and ask as many questions as you can. The point here, we have 5 days to present. I have 5 days to present everything, almost 8 hours of lectures, so please feel free to interrupt as many times as you would like. Also, in my webpage, I'll put the basic references. The references from each lecture. Okay, so basic papers and lecture notes from other courses and so on that are necessary to follow what I'll be presenting here today. My plan is to have, by the end of the week, lecture notes as well, but I cannot promise that. It's not converging very fast, so I don't know. But the website definitely will have the homework set and references, okay? All right, so now let me start by telling you what Floquet engineering is. So the title of this course is Floquet Engineering Quantum Systems. I'm assuming that you know what a quantum system is. So I have to tell you what Floquet engineering is. Maybe you know also what engineering is, but maybe you don't know who Floquet is. So let me start by telling you what this is about, okay? So this course will be about Floquet engineering. And before I tell you the details of what this is, let me just give a broad syllabus of what I'll be covering here in 5 lectures. So today I'll be giving the basics, so what is also called Floquet theorem. And maybe, I don't know, I will put some topics here. It doesn't mean that I will cover one topic in one day, but this is how we are going to proceed. So tomorrow we are going to talk about Floquet engineering band structures, and we'll touch on topological insulators and quantum Hall effect. This is the topic of tomorrow. And then we're going to talk about Floquet plus strong correlations. Strong correlations. And here, I will spend a little bit of time defining these systems. Maybe not everybody is familiar with the particular physics that I'll be covering here in topic 3. We are going to talk about Kondo systems. We'll be talking about Hubbard models. So this will take a bit of our time. And I consider this to be the basic topics that I think are extremely necessary to cover in this course. After this, there are many, many possibilities. One of them that I will probably cover is what is now called quantum light. So it's the same things that we're going to do here in 1, 2, and 3, but considering the limit of few photons, or beyond the limit of coherent states. So this is going to be quantum light. And maybe out of equilibrium as well, maybe. This is already maybe out of equilibrium. Out of equilibrium physics, okay? All right, this is just an overview of what we will be covering. Now let's start talking about topic number one. So topic number one is the basics of this field. So as I was telling you before, maybe you are not familiar with the concept of Floquet engineering. So let me start by introducing you to Floquet, who Floquet is. So this name Floquet comes from a French mathematician. So his name is Gaston Floquet. Gaston Floquet. So Gaston Floquet was a French mathematician. He lived in the late 19th century. So second half of the 19th century, so to be more precise, between 1847 and 1920. And Floquet, as a mathematician, was worried about properties of differential equations. And in particular, what we're going to address during this lecture regards one of the works by Gaston Floquet. And I will put the title here so that you have an idea of what we are going to be talking about. The title is this: Equations. I'll put the name, this is the original name in French. So this already gives you the flavor. These are differential equations. They are linear. And they have coefficients that are periodic. Okay, they are periodic. So Floquet was interested in properties of linear differential equations that are periodic in time. And that's why we care about this work, because we're going to be talking about quantum systems here today and over the next lectures, and we're going to be talking about very specific quantum systems, the ones that follow Schrödinger's equations, basically all the quantum systems. And as you may recall, the Schrödinger equation is a linear differential equation. So far so good. These are linear differential equations. And, but you may say, well, but typically the Hamiltonian is not a function of time. The Hamiltonian is just matrix, an operator. So we are used to Hamiltonians, operators, that are not explicit functions of time. Obviously, the evolution over the Hamiltonian is a function of time. You have unitary operators that are going to in time, and these operators will be functions. The unitary operators, the evolution operators will be functions of time, but not the Hamiltonian itself. But in this course, this is different. In this course, we are going to consider Hamiltonians that are explicit functions of time. So this week, we're going to have Hamiltonians which are functions of time, okay? Which are functions of time. But they are very special functions, and from the name that I just gave you here and the title of this paper, you can already infer that these Hamiltonians are actually periodic in time. So these are Hamiltonians that are periodic in time, okay? So we are going to consider systems. These are called driven systems, because now the Hamiltonian is an explicit function of time, a periodic function of time. The two questions that you can ask at this moment are, why would I consider Hamiltonians like this? So why? Why do I care about Hamiltonians like this? And the second question is, okay, let's assume that I want to solve this problem. How do I solve this problem? How do I solve a problem with a Hamiltonian which has a time dependence that is very special? This time dependence is very special. How do I solve it? And we're going to go back, in a sense, to Floquet's original paper. The answer is there. It's a mathematical paper. At least the basics is there. We are going to, of course, on top of that, we want to get some physical intuition of what's going on. So this is the task that we are going to have during these 5 lectures. But now let me start by telling you why would we care about this. So why would I consider a Hamiltonian that looks like this? Okay, and the answer follows quite closely from the previous lecture, from José's lecture. So I hope from José's lecture that you are convinced that phase transitions, classical quantum, thermal phase transitions are extremely interesting. And in particular, there are some phases of matter that are particularly challenging to describe. This week, we're going to be talking about several phases of matter. We're going to be talking mostly about the ones that are very challenging to describe. They're not simple. The simple ones, over the last decades or the last centuries, we know how to treat simple. They don't necessarily have to be simple. I'm defining simple as something that we know how to solve. But there are many phases of matter that we don't know how to solve. And the point of this course, my course here, will not be solving these models. I will not be solving the models. I will be trying to engineer these models. So this is the second half of our title here. I'll try to engineer models that are hard to solve. Then you can ask, but why would you do this? Because, end of the day, we want to describe the most interesting phases of matter. And sometimes these very interesting phases of matter, if you have phase diagrams, so in the last lecture, you saw many phase diagrams. You saw the phase diagram of a simple fluid that had like solid, liquid, and vapor phases. You saw the phase diagram of magnets. There are many, many other possible phase diagrams. But what often happens is that the most interesting phase, so if I put a phase diagram here with some arbitrary axes, let's call it x1 and x2, it often happens that the most interesting phases are confined to tiny regions here, tiny regions. And this is not only a theoretical thing, an experimental statement as well, that you often have many phases of matter that are quite intriguing, quite interesting, almost very challenging to describe, but they are here in tiny regions of phase diagrams. So it will be extremely desirable if we could just come to these tiny regions of this phase diagram and zoom in. And we are going to see that the proposal of this course here will be exactly that. We are going to find new parameters. So Floquet engineering, so the point is this, Floquet engineering provides new parameters to probe phases of matter. This is the main motivation of this particular course. Okay? New parameters. In a moment, by the end of this lecture, I expect you to know what are these new parameters. Okay? What are these new parameters? Typically, experimentally, you have access to pressure, you have access to temperature. So in experiments, typically you have access to things like temperature. You have access to mu, the chemical potential. So temperature, as you saw from last lecture, is an important knob, an important parameter in phase diagrams. And you can easily increase temperature experimentally. This is not very challenging. Chemical potential, you can also do it by doping. You can have a voltage difference, and that will lead to doping in your sample. This is something that can be also accessed experimentally. But in this lecture, I want to talk to you about interactions with periodic potentials. Interactions with periodic potential. This is going to open up new doors to construct phase diagrams that are analogous to these ones, but instead of having a tiny region here of interesting physics, it may have other axes like y1 and y2, in which this interesting phase becomes very large. This is the point, okay? This is the main point here. I want to go to phase diagrams, and I want to go to probe phases that are very challenging to describe theoretically, and that are also very challenging to find experimentally. But these are by far the most interesting ones. These are the ones that we're interested the most. Okay, so this will be our motivation. We are going to have to pay some prices for that. Okay, it's not for free that we're going to get here. So this is the idea if we include external potential. external potentials. This is the gain. This is what we gain. Now we have this wonderful big phase of matter here that we can, in principle, probe. But there are several things that we have to take care of. The first thing is, we have to find this phase. So we have to solve this. We definitely have to solve this Hamiltonian. We have to solve this. This is a price that we have to pay. Okay? And in today's lecture, I will be giving you the basic ingredients to solve this Hamiltonian. It's not going to be the complete solution, of course, because I could tell you a Hamiltonian that is not a function of time, that is very hard to solve. And if you make the same Hamiltonian a function of time, it becomes harder to solve. So I'm not going to be solving all problems. What I'm going to be telling you is how to handle a Hamiltonian that looks like this, okay? Based on what Floquet did in the 2 centuries ago almost, okay? Do you have any questions so far about the motivation of what we're going to be doing here? Okay, we are going to be engineering systems using time-dependent Hamiltonians based on Floquet theory. Okay, this is the basic strategy. And again, over the next lectures, I'll be going through several examples or several interesting cases, okay, one by one. Band structures, how can we do it? Strong correlated systems, how can we do it for Kondo systems, for Hubbard models? And I probably won't have time to talk about, but maybe Fernando will talk about it during his lectures. There are some phases of matter that don't even exist here in this phase diagram, but it would exist here. One such example is time crystal. Is a time crystal in equilibrium in a system like this, not found. But in systems that are driven like this one, you can find crystals that are not periodic, don't have the proper periodicity, not in space as we know from regular crystals, but periodicity in time. I probably won't have time to go through time crystals, but it will be a natural number 6 here, okay? It will be a natural number 6. So this is very complementary again from what José is telling us during the morning about how amazing phase transitions and phase of matter are. Now it's a question of how to find them, at least theoretically, how to find them in phase diagrams, okay? What I'm going to be telling you here, so even though Floquet's theorem is from 2 centuries ago, what I'll be describing here really exploded over the last 20 to 30 years, let's say. Over the last 20 to 30 years, this field became gigantic, partially because it's now possible to measure experimentally what has been proposed here, okay? These are not only theoretical calculations anymore, but possible to probe experimentally and to see in a lab that you can actually access these phases of matter. So this is an experimental reason why we would care about this, okay? All right. Let's start by doing some theory then. Let's see what we can do to solve this Hamiltonian. I will be drawing many analogies with quantum, with solid state physics. If you want to solve Schrödinger's equation, and if Schrödinger's equation is periodic in position, not periodic in time, you know how to solve this equation from solid state physics. Even if you don't at this point, because you didn't take solid state physics, I'll be telling you the basics. It's quite analogous, but it's not identical. It's not identical. The two things are not identical. But Bloch's theorem is basically a manifestation of Floquet's theorem for real space. Some books even call this nowadays Floquet-Bloch theorem. Floquet-Bloch. There is no question that Bloch did it after Floquet, 40, 50 years after Floquet. There's no question about it. In a slightly different context, but it's the same, mathematically the same problem. It's a differential equation that is periodic. In the case of a crystal, it's periodic in position. In the case of this lecture, the Hamiltonian is going to be periodic in time, okay? All right, so let's start by doing some of this so-called Floquet theory. So this is topic number 1, finally, okay? All right, so let's consider a Hamiltonian of the following form. H of t is periodic in time. There is a frequency that is associated with this period, so 2 pi by omega, okay? There is some frequency here. And what I would like to know first is what are the solutions of Schrödinger's equation for this problem? And again, I will not be able to solve Schrödinger's equation and give you that the energies are 10, 20. This is not the point. I just want to recast Schrödinger's equation in a proper way when this Hamiltonian is periodic in time. I just want to rewrite it and manipulate it using this fact. This is what we're going to do first today, okay? Very good. All right, so Schrödinger's equation again, and today until, I don't know, I don't promise the entire lecture, but until noon at least I'll be writing H bars. But the H bars will eventually disappear, probably in a not very consistent way. It will reappear. I was just checking that some of my equations, some H bars are missing some specific factors, but not in other factors. So if you find a missing H bar, please let me know. I will try to use H bar through this derivation, okay? All right, so Schrödinger's equation is like this. In general, this is the general form of Schrödinger's equation. And this is just the first derivative with respect to time, okay? This is the general form of Schrödinger's equation. Of course, we cannot easily solve it, as it is often the case. But let's now use explicitly that the Hamiltonian is a function of time that is periodic. So if the Hamiltonian is periodic in time, H can be written in this following form: sum over m, Hm, e to the minus I omega mt. Where these are operators as well, but this m runs from minus infinity to infinity in principle. Some of them can be 0. But as you may have noticed, this is just the Fourier series of this Hamiltonian. This is the basic strategy. Fourier also helped to solve the same problem. I mean, we also get help from Fourier to solve this problem. It's obvious that if you boost time by big T, you get the same thing. Let me just do it here. Hm e to the minus I omega mt e to the minus I omega m big T. But again, omega big T is 2 pi. So the Hamiltonian is the same as before. And these m's are integers, okay? So far, just decomposing the Hamiltonian in harmonics, if you will, okay? This is almost nothing so far, but let me tell you what is the structure of this equation. Let me call this equation 1. So the solutions of 1, they have the following form. So this is the theorem. Then what I'm going to say next is the theorem. So the solutions of 1 have the form all right, maybe I'm not ready to write the solution just yet, maybe in a moment. Okay, phi a of t, let me just write it down and then we check. Phi a of, it's e to the minus I energy time divided by h bar, sum over n, e to the minus I t n, divided by h bar. No, there's no h bar here. Omega tn phi a of n, okay? This is the theorem. It says that this equation 1 has solutions that have this particular form, okay? This particular form. We have to understand the meaning of all these terms at this point. All right, so the first thing that I will tell you is that EA are called quasi-energies. Quasi-energies. Quasi-energies, okay? So these are the quasi-energies, and this function is not explicitly periodic in time, okay? And again, this is We are going to talk about crystals in a minute, but this is completely similar to what you find in crystals. So this will be the analog of these Bloch wave functions, okay? In which they have a term here that is completely periodic in time. So this is periodic in time, and a phase which is not periodic in time. So the analogy here with crystal, remember, if you have a crystal, momentum is not a good quantum number. Because if you only have translations in real space by vectors, by very specific vectors, right, that take you from, let's say, one point to another point in another unit cell. Here is the same thing. The Hamiltonian is periodic in time, but energy is not a good quantum number. What is a good quantum number in a crystal are these quasi-momenta. So in a crystal, you may recall that the momentum is conserved up to a reciprocal lattice vector. We are going to find something analogous here, that the energy is conserved as well, up to something. This something will become clear in a moment, okay? But please keep in mind the complete analogy, if you took solid-state physics, of this, what I'm telling you here, with Bloch's theorem, okay? I will even write it here. So in solid-state physics, you have, let me try this guy here. Solid-state physics, you have this psi k alpha of r, which is a plane wave, u k alpha of r, okay? This will be the analog of this. And again, this k is the quasi-momentum that is conserved up to these reciprocal lattice vectors that we typically call G, okay? And here we have a phase as well, and we have something that is periodic, clearly periodic in time. You can see that if you take t to go to t plus big T, this function remains the same, but this function does not remain the same. And here I'm using this label as well, this label A. And so far I will just tell you that these are to label eigenstates. It will become clear later. So the first thing that I will do after finishing this derivation, I will solve a spin 1/2 problem. The simplest quantum mechanical problem that you can imagine. You solve a spin 1/2 problem and you apply all this technology. So if you think this is a bit too abstract at this point, just some algebra, we are going to solve a spin 1/2 problem in a minute, or in half an hour, and then see how we can apply this explicitly, okay? But the label A will label eigenstates that is analogous in a spin 1/2 case, the up and down. This will be, but the eigenenergies associated with these two labels, okay? Do you have questions so far? Okay, so what we have to do now is we have to take the solution 1, the solution 2, and check if 2 is a solution of 1. Okay, this is what we have to do. It's just some algebra, but we can do this algebra together. Please let me know if you find a minus sign that is missing somewhere. Okay, so h of t applied to this function here, phi a of t, it's going to lead to the I times the derivative h bar, derivative with respect to t of the same function here. E to the minus I e at divided by h bar sum over n, e to the minus I t n h bar phi a of n. Okay, it's just a simple algebra that we have to do. So we can start. Let's also, the first thing we have to do is to write the explicit form of the Hamiltonian. Otherwise, this equation in principle would be valid as written here for any Hamiltonian, but we know that's not true. It's only true for periodic Hamiltonian. So let's use this equation here. So this is sum over m, hm, e to the minus I omega mt, e to the minus I eat divided by h bar, sum over n, e to the minus I t n omega phi a n. Okay, so this is this side of the equation. And the other side of the equation is I h bar. And then I can take the derivative of these two terms, minus e a divided by h bar, sum over e to the minus I EAT divided by h bar, sum over n, e to the minus I omega t n phi a n. This is the first term of the derivative, and now I have to take the second derivative of the second term. All right, plus, or sorry, minus I omega e to the minus I EAT divided by h bar, sum over n e to the minus I omega Tn phi a of n. Does everybody agree with this last equation here, just taking the derivative? So we have the derivative of this term times this, derivative of this times this, and of course this is time independent. These are basically the Fourier components of this function, okay? So I'm just taking the derivative of both terms, and now we can already see some cancellation. And at this point, you may already know where I'm leading to. I want to find an effective equation for these Fourier modes. I want to see what is the equation that these guys would satisfy. So I will find a time-independent. What I propose here is to find a time-independent equation in terms of these Fourier components. This is my task here. Okay, and it's looking promising. If it doesn't work, if I still remain with a time dependence here, we can blame Floquet. The theorem doesn't work, but it will work. And we're going to find a time-independent equation for these coefficients here. All right, so let's cancel this and this and this. And I will go there and write what is left from this equation, okay? Okay, so if we just take what is left from that equation, we have a double sum here over m and n, and we have a sum over n in both terms here. And again, this is time dependent. All these terms are time dependent. But as you may recall, when you have time dependent oscillations like this, it's like a Fourier series. So there is a very standard way to remove this time dependence here, okay? There is a very standard way of removing this time dependence here. Does anybody have any suggestion about how to make this equation time independent? How to remove these exponentials from here? No suggestions? How to remove the... We have a completely time-dependent equation here, okay? This equation still oscillates. We would like to find an equation that is time-independent, but just in terms of these HMs and the Fourier components. So the question is the following: how to come from an equation like this, that has these oscillations, to an equation that doesn't depend on time at all? Yes, this is already almost Fourier transforming, but yes, we have to find the coefficients of the Fourier transformation. And for that, we can just take both sides of this equation and integrate. We can just take multiply both sides. So take both sides. And you multiply by 1 by t, that is the period, you integrate from 0 to t dt, e to the I L omega t. So this is a filter. It will filter. So when you do this, only the combinations here that don't oscillate with frequency, or only the components that oscillate with the same frequency as that one, will survive. So these filters. And end of the day, that will make this equation time independent for the Fourier components, okay? So just doing that procedure, you'll find the following: h bar, sum over n, EA divided by h bar, plus omega n, 1 by t, integral from 0 to t dt e to the minus I omega t n e to the I L omega t. So I'm just multiplying the term. I'm multiplying actually the term from the right first. So the rightmost term first. And this is equal to 1 by t, the period, sum over m and sum over n, 0 to t dt, e to the minus I omega m plus n minus L times t. Okay? You can check if I'm not cheating by not considering the terms properly, but if you do the multiplication, you should end up with something that looks exactly like this. Okay? All right, so from here, we can already see that this term, what is missing? Oh, sorry, HM is here. So the first term has HM, this HM is here. And also I'm missing the state, that is even phi AN and phi AN, okay? Is there anything else missing? I mean, does everybody agree with this form of the equation? All right, so this first term leads to a delta function. L has to be equal to n. And this one is a delta function that m plus n minus L has to be 0. Okay? It's just Fourier decomposition, really. But what is interesting, we are going to draw a picture showing what's going on in a minute. But for now, we need to find what is the equation for these HMs. So after this, this implies that H bar, EA divided by H bar, plus, after this L is an external index. Okay, so the L will remain L omega, phi A of L is equal to sum over n, H, L minus n, phi A, n. Okay? Check it. Please check if you agree with this from here to here. All right. In terms of the theory, I just did all this algebra together with you to show this final equation, because this is, end of the day, that the equation that we're going to be analyzing the most through this week. So far, the only thing that happened is that we had a Hamiltonian that was periodic in time. We decomposed this Hamiltonian in terms of Fourier components. But the Fourier components are all mixed. They are all mixed. That's the price you pay. Okay, if you diagonalize a Hamiltonian without time dependence, it's not obvious that after you put some time dependence, you're going to have the same eigenstates. Probably you will not have the same eigenstates. But this is the equation, now the Schrödinger's equation, that has to be solved. Okay, this is the equation that has to be solved. We would like to solve for the quasi-energies. So we would like to find the states, and we would like to find the quasi-energies. Okay, this is the task that we're going to be facing this entire week. And the point is, for each system that we are going to consider, we're going to start with something that is relatively boring, and then we are going to follow this prescription, find the eigenstates of this equation, and then we're going to get something that is interesting, or more interesting than before. Okay? So this is the way we're going to proceed. All right? Questions so far? Mm-hmm. Right. It depends. In principle, the answer, the generic answer would be no, because the same way as you have some time evolution operator, it gives you some phase to a wave function, but not all phases are Berry phases, right? Sometimes you just have time-dependent phases. So the generic answer is not exactly, but it could be that this prescription may lead to Berry phases, but not at this stage, later. It could be that this Hamiltonian here is a topological Hamiltonian, or this equation has Berry phases, but so far, from this, no. From this, it's just a evolution with time of a particular state, okay?
I'm not sure if I understood the physical picture of the quadrant. Doesn't it depend on the track frequency?
We're going to see that in a moment. Right, so recall, I will try to answer the question in a simple way now, but we are going to come back to this question several times during the week. So if you have like some vector k, quasi-momentum, this k, if you add a reciprocal lattice vector, momentum is conserved up to this vector. All that I'm saying here is that if I solve this energy, for this energy, I find these energies here, okay? If I add up some multiple of this frequency omega, we're going to see this here. It'll be, this thing has the same role as this thing here, okay? So that in that sense, they are similar. But this will become more clear, I think, with the spin half case. But that's what I mean by quasi-energy, in the same way as K in a crystal is a quasi-momentum, because it's not complete, it's conserved only up to reciprocal lattice vectors. Here, the energy, quasi-energy is conserved up to some number, we usually call it some number of photons, even though it's a classical description. But we are going to come back to this question. Yeah. Right. Yes, absolutely. Oh, we are going to come to this question tomorrow or the day after. So the question is this: the Hamiltonian is time dependent. So there is this. I started talking about this guy, but then I immediately stopped talking about this object here. Okay, this object here. So the question is using. So of course, if you go to a lattice and you can do these translations in a very specific way and so on, and from symmetry arguments or group theory arguments, you can conclude what are the values of these G's and so on. So here we're going to see that the same role will be played by this time evolution operator. Because one thing is to find this Hamiltonian that it doesn't depend on time, but then you can ask, how do I evolve this system in time? Do I just, one guess would be just take this so-called Floquet Hamiltonian and evolve it. But is this correct? We're going to come back to this question later, but the answer to the question is absolutely yes. There is a way to find all of this from symmetry arguments, for sure, the same way as for the crystal. Any other questions so far? The same way as for the crystal, if I were solving a crystal, I would also start like this, not from the group theory. The same way as here, but absolutely, it's completely equivalent. In which what was that? Did you say absolute aspect? What was the last sentence? Uh-huh. Right. In general, absolutely. Yes, that's an important point. So here I'm taking this and plugging into this equation, okay? So I want to know about this equation, okay? But in physics, you have many other possible equations. In particular, in classical mechanics, for example. You can have a pendulum, let's say, and then you just want to start hitting the pendulum periodically with some force of some sort. how do I solve this? I mean, we can take the equivalent equations in classical mechanics and try to see the behavior using the same theory. Using the same theory. You can absolutely kick the harmonic oscillator and so on, and use the Floquet theorem to solve the driven harmonic oscillator, for example, or any others. Yes, that's right. Okay, any other questions? All right, so now I think we are ready to start analyzing this, what we found. All right, so let's see. So it may look very abstract, what we found here, just a bunch of indices and so on. So let me give you some perspective of what this is. So let me represent this schematically. And again, if you have a problem that is simple enough as a function of time, you may just solve it. I mean, you don't necessarily have to come to all the steps here, but we're going to see with the spin half that it really works. Okay? All right, so what we have is, let's say I want to represent this equation as a matrix. This is the first thing that I would like to do. Okay, so the matrix, the Hamiltonian matrix now is going to be very large. So it's like this. So if I this is an equation acting on this cat, so I can write as a full matrix. So it's going to be like this, H0 minus omega, H0 plus 0 omega, why not? H0 plus omega. But it never ends. This matrix never ends. And it's completely populated. So here with this notation, this is H. All these guys have hats, so this is going to be the identity matrix here. This is H minus 1, H minus 1, H minus 2, H 1, H1, H2. Okay? This is the matrix that we have to solve now. So again, even if we have, let's say, a simple spin half problem. A simple, well, it's a bit tautological, simple spin half problem, but okay. It's a spin half problem. If you have a spin half problem, you're going to have two states, and then you can find the eigenstates and so on. But even for that spin half problem, it's not completely obvious that you're going to be able to diagonalize this gigantic infinite matrix now. Okay, this is the task that we have to do. We have a spin half problem that is plus, let's say, a periodic drive. We call it a periodic drive. Something is driving the system, okay, out of equilibrium. Then we have this matrix like this, and for a spin half, for instance, each block, or each Mn, is 2 by 2. So each Mn is 2 by 2. Okay? And then the task is to diagonalize this Hamiltonian. As you can see, with this matrix here, this equation becomes an eigenvalue equation, okay, for the quasi-energies, okay? So you can solve this H, this very big vector here, equals to this, where the arrow now represents Floquet space. We call it Floquet space. So the way to interpret this matrix, let's say here, I'm going to give you some jargon of this field, how people talk about these things. So this is considered the 0 photon block. This is the -1 photon block, and this is the 1 photon block. No, yes, this is going to be the block. The block, yeah. This is the state of that is emitting 1 photon, let's say, and this is the block. So -1, 0, 1, and so on. 2. Okay? So we refer this to these photon states, even though the field is it's classical. These are Fourier components, okay? All right, so and to represent this schematically, notice that even H0, this is a common thing, even H0 is not the original Hamiltonian. Okay, these are the Fourier components. In particular, if you come here and ask what is H0, H0 is the component with m equals to 0, so it's the average over time of the Hamiltonian, okay? So what H0 in particular, just to give you, it's going to be important. The most important, all of them are important here, but we are going to see by doing perturbation theory and other things that the most important ones typically are H0, H1, and H minus 1, typically, but sometimes all of them. In particular, H0 is the time average of this Hamiltonian. Okay? And so on, and the other are the Fourier components. Just to not lead you to the idea that H0 is some Hamiltonian that is something else. I mean, this is the time average of this Hamiltonian. Okay? And finally, if I represent this schematically, so I can, let's say that I'm able to solve this Hamiltonian H naught. The point is that this matrix is connecting all of them. Therefore, this guy here is H2, for example. So it connects some sector here with 2 plus. So you go from here to here. This guy connects from here to here, H1, and then there's H minus 1, and so on. So if you think of your system as some system, let's say this is let's say graphene, for example. We're going to consider 2D graphene. And then you think, oh, I can solve graphene. But now we have infinite copies of graphene, and all these copies are connected. Okay, so even in systems in which it may be easy to solve the time-independent problem, when you put here, and here I'm representing schematically energy, but it's completely schematic. All these systems are now connected, so I have to diagonalize everything again. Okay, even if everything was nice and diagonal, but now this is no longer the case. Okay, this is no longer the case. So there are several ways of representing the same thing. This is the equation that we have to solve. This is the form, matrix form of that equation. And this is the picture that represents that equation. But in any case, this week you are going to be solving or trying to solve Hamiltonians like this using very specific time periodic potential. Okay? So the theory is basically up to this point. Now we have to just work and see what we get. The only theoretical thing that I will be doing still, or I'll be doing other theoretical things, but for next lectures, the time evolution operator is still, we are going to come, it's a little more, a bit more subtle, but we'll come back to how to evolve these systems in time, okay? Questions? Continuous space? No, it's a discrete space. It's like, the closest I would say are the levels of the harmonic oscillator. Like, think of the harmonic oscillator. So the level, but here it can be negative as well. But 0, 1, 2, 3, these are integer numbers. Infinite number, but all integer numbers. It's not continuous. It's a discrete, infinite discrete set of discrete values. Know if the function that you're transforming is periodic in time. It's the same as when you do like, it's not, remember Fourier series. This is more like a Fourier series because it's a periodic thing, so you can just decompose as multiples of some harmonic. 1, 2, 3, 4, 5, and minus 1 because you have, like, these are exponentials, right? So you have sines and cosines and so on. So it'll be more analogous to the Fourier series, not the Fourier like transform with all the, okay? Because this function is periodic in time. So what was the last part of the question already? No, here? This one? No, not yet. No, I mean, I know. Okay, it's going to take some time to zoom in. I mean, zooming in is like the last thing, if possible. It's many steps until we zoom in. That is the final goal. That is the final goal. But no, so far what we are doing is taking a problem. It could be a problem that we know how to solve, and we're making it more complicated, in a sense, and expecting it to find interesting physics in the middle here, okay? I can give you the example of graphene already. I'll be solving this example tomorrow. You take graphene, nice and simple, and then you apply circularly polarized light. And then the graphene will, the effective model will be of a Chern insulator, the Haldane model for graphene. And this was measured experimentally. So this is one of the simplest solid state proposals, starting from something, not the graphene is boring, but let's say you start with graphene and find something more exciting, that is the Chern insulator, okay? Okay. Mm-hmm. End of the day, I'm representing this matrix schematically. So you can just think of this matrix as some sort of tight binding problem in which you have hopping. So you start here, you have some levels, very nice levels. They are eigenstates of this guy. But then they hop. So they are not eigenstates of this full thing. So here you can think of solving H0 in each block, but now they can hop. So you can think of this is almost as a chain along this direction. Yeah, for instance, the eigenvalues of H0, it's just schematically. But let's say that you find nice levels here, nice levels here, nice levels here. You think, well, I'm done. Okay, but they hop. I mean, this H1 is going to connect this layer with this layer and so on. So you have to rediagonalize the problem same way as if you solve for a single site, and then these electrons or whatever, they start to hop, and then you have to solve again. Okay. Yeah. We are going to have several, again, we want to find interesting physics. Typically, we cannot solve the time-independent problem, and then we make it time-dependent, and it's just much more complicated than the problem that we already don't know how to solve. So we are going to be definitely doing perturbation theory several ways. The simplest that I may be able to talk about today or early tomorrow is this high-frequency expansion. This is one way. There is also the low-frequency expansion. As usual, we know more or less how to solve the limits. So if the frequency is very small, the frequency is very large. The problem is when the frequency is not very small or very large. Okay. So just to tell you what is a bit challenging when we are really comparing these interesting phases with experiments, if you think of this model, and again, this is schematically, but it's not so schematic. So if you think of time, and then you think of this axis as distance to equilibrium, a distance to equilibrium. In principle, if you have a time-independent problem, let's just say that you have a sample, you're going to measure something, like magnetization, specific heat, or anything. You are in equilibrium. So you start here, you are in equilibrium, very nice. Nothing happens. You don't need today's lecture. Not this lecture, you need the early lecture from José. All right, but then you start applying this field, or and then the idea is that you come here, and then you decay. This is called the Floquet plateau. Floquet plateau. And the idea, why would you have a plateau like this? Is because here you don't have the periodic potential, and here, experimentally, you're going to have a pulse. So this is a pulse. Okay? So this is what happens, so let me say, this is what happens in practice. In practice. So if you go to any lab, you don't have like lasers running from -infinity to +infinity in time. What you have is a pulse. And this pulse may look periodic for some time. It's not completely periodic, of course. It has some envelope here. It has the envelope. And end of the day, what the pulse has is a finite energy density. So if you want this amplitude to become larger, the pulse is going to become shorter in time, and so on. So this is the It's the electrodynamics, the energy that you have for a pulse of light. For example, I'm always using light as an example. This is the most common example, but I'll be talking about many other things. You can literally take a sample in your lab and start in doing this. You just shake it. It's also possible. You're oscillating it over time.
I could understand what you have in mind. What's in practice? What's this yellow line that goes up and then comes down?
Right, okay. Okay, let's try again. Let me be more pedagogical about the line. So this yellow line is the distance to equilibrium. Distance to equilibrium. The Floquet state is not an equilibrium state.
You start in equilibrium.
Yeah, you pulse. This is what in a lab would happen. For us, you have this thing forever, and you have the Floquet plateau forever. This is our thing here in this week. This week you have started in minus infinity, plus infinity, and we're going to see that this plateau that is here survives forever by construction, because I'm not putting anything here that would destroy this plateau. But we can discuss next lecture what would destroy this plateau. Okay, but so this is in theory, what happens in theory. This is what happens in theory. In theory, you have some oscillation, like it can be a chemical potential oscillation, a mechanical oscillation, light with a given frequency, anything. It starts minus infinity and plus infinity, periodic forever. In a lab, you have your sample, and then you shine some pulse of light, for example. So you were here, and now you have this pulse. So this pulse, you do this technology here. You're going to be making mistakes when you do this, because it's not completely periodic in time, okay? But the idea is that there is a region here in which this Floquet plateau exists. Just to give you the example of the graphene, this would be like, let's call it standard graphene. Standard graphene. Standard graphene is a 2D sample, honeycomb lattice with 2 direct cones. Okay. And then we start shining some light. This is what they did in a lab, like 2020. They were able to measure what I'm going to be describing here. So you shine a pulse, and then you expect this to have this effective model. So this will have an effective model. Effective model. And in graphene, this is going to be the so-called Haldane model on the honeycomb lattice. And then you do other measurements here. During the same time interval, you do some measurements. You put RPS to measure edge states, you measure transport, you measure something else to see that you are here and not here. This has to be measured, okay? And then we concluded that, okay, experimentally, this can be probed. This can be probed because we see the effective physics here. But again, this is not an equilibrium state. We are pumping, the Hamiltonian is a function of time. It's like a driven harmonic oscillator. And it could be that the system can start absorbing energy from the source. You shine some light, and then the electrons, if you do this, for example, you have a metallic sample, the electrons are just going to be extremely happy and move around with that energy. Okay. But so this is, and I'm not going to be describing much of this part here, maybe on Friday, maybe. And this is the thermalization part. I'm going to even write thermalization or else. Something is going to happen here. Thermalization may be a possibility. If you have, for example, graphene, you may have phonons, you may have other things in your sample, and these things can transfer heat. So it can destroy this plateau. Because this is, okay, let me be more precise. I'm going to assume this is a Haldane model at t equals to 0 as well. At t equals to 0. Okay, go. Yeah. I'm going to assume that, okay. Okay, so, okay, let me go one step back. The Hamiltonian can be like, let's say, periodic in position, but we're not talking about that, right? This is something else. I'm going to assume that the Hamiltonian, the complete Hamiltonian is periodic in time. It's not that I have a Hamiltonian plus something that is periodic. The entire Hamiltonian has this periodicity, okay? This is the only time dependency that the Hamiltonian has. It cannot be like, oh, the Hamiltonian, there is periodic plus something of time. This does not exist, okay? It's just the entire time dependence of the Hamiltonian comes from this equation. Nothing else, completely periodic. Completely periodic, we can do this technology here. Everything that I did is completely exact. I didn't do any approximations, anything. This is completely exact. Doesn't mean that I'll be able to solve this. I probably won't, from most cases. Completely exact. I'm just bringing back the lab, what you actually measure in a lab. In a lab, you don't have this forever. So I just want to emphasize that what you want is to measure something in this plateau here, okay? In this plateau. This is the interesting plateau. More or less, let me see if I understood. You have this Hamiltonian in equilibrium. This is what you have. But now we are going to have some delta H, which is an explicit function of Tiba periodic. Is this what you mean? Yes, in general, more or less like this. It could be that the time dependency becomes a coefficient here. It's not plus necessarily. I will make Hopkins time dependent. I will be making chemical potentials time dependent. So parameters can depend on time. And also, I mean, the expectation here of having a plateau is different from quenching, like this, doing something abrupt. Here is not the dynamics of something abrupt. It's the dynamics of something that is periodic forever. Okay. Questions? Mm-hmm. Mm-hmm.
I'm picturing that in this plateau you have another state.
Another Hamiltonian.
Another Hamiltonian, okay, but also all equilibrium one, and you keep there.
Mm-hmm.
That's what the plateau one
Mm-hmm.
is on. That's the control part.
Yes, exactly. So you exactly.
Actually taking from here to here and keep it there.
Yes. Yeah, it's very challenging, experimentally challenging, not impossible. You shine some laser, so you take a sample like graphene, you shine some laser, and then it makes you here. So let's see. But then you have to measure something else, because now you have a new state, as Rui is saying, you have a new Hamiltonian, correct, but also you want the ground state of this new Hamiltonian, the ground state of this new Hamiltonian. And then you have to measure something from this ground state, like the Chern number corresponds to the edge states. I want to measure edge states. How? I'm going to measure sigma xy during this plateau. And it's possible, it was done. This is possible. Okay. Sure. Mm-hmm. Sorry, can you repeat? Mm-hmm. No, there are many possibilities. One would be to have some laser shining. If you can find some source of light that is monochromatic, that is phase coherent, and the sample is not going to heat up, because there is the pulse duration, and there's also all the things that are going to happen here as well. This starts to kick in as well. In particular, you can have excitation, so this is not going to be a ground state property anymore. So now you are in a thermal state. But yes, you need a coherent source of monochromatic light. This is typically done with these lasers, okay? All right. Very good. Okay, so now let's solve one simple problem, that is the spin half problem. So the spin half problem that we are going to consider as an example for the last minutes or last 20 minutes of this lecture is going to be of the following form. Consider a spin half problem. Okay, so the Hamiltonian is going to be an explicit function of time, bz sigma z plus b parallel sigma x cosine of omega t plus sigma y sine of omega t. Okay? So this is the Hamiltonian that we want to solve. Well, first thing you can say, well, I don't need this lecture to solve this Hamiltonian, right? This is in Cohen-Tanuji or any quantum mechanics book. The point here is to use this approach to solve this problem. Tomorrow, we're going to solve it again using this rotating wave approximation. In this case, it's exact. We're going to a rotating frame to solve this Hamiltonian. Clearly, this Hamiltonian is rotating. Clearly, it is rotating. It's rotating in this xy plane, okay? All right, but we can, for today, we can solve this Hamiltonian using the technology that we just learned. All right, let's do it. The first thing that we have to do, so it's always like this. It's always going to be like this. It's like step number one. Step number one, find HM. Find HM. Hopefully this is possible. If even this is not possible, then it's not great. All right, so what is HM? HM is 1 divided by t integral from 0 to t dt of what? Of e to the I m omega t bz sigma z plus, and here I'm going to write, it's already better to do it this way, 0 e to the minus I omega t, e to the I omega t, 0. That's it. Okay? All right, we can integrate this easily. Okay. It's just a matter of integrating it now. Clearly, this term is time independent. So this is an example of what Joe was mentioning, because you have something you could say, I have just a magnetic field along Z, but now I'm adding something to the Hamiltonian. So this is one example where we're adding some oscillating field in the XY plane. Okay, so what are the components of this Hamiltonian? The components are the following. It's just a matter of integrating. So this is equal to what? This is equal to Bz delta of M0 plus B parallel delta of M1 0, 1, 1, 0 plus delta M minus 1 0, 1, 0, 0. That's right, thank you. Sigma Z. All right. Very good. All right. Very nice. And now this problem has, okay, not all of them, some of these guys are finite. So we can come here and construct this matrix. Okay, we can construct this matrix. When we construct this matrix, all of these people are going to be 0. And all of these people are going to be 0. Okay, so it's going to be something that looks tridiagonal, but not really, because it's 2 by 2 inside. Okay, so the Hamiltonian, step number 2, write H. So H is equal to what? This is, here I'm not being very careful. Let's put some symbol, some HF, as in Floquet here, just to give credit to Floquet. So let's write the Floquet Hamiltonian. It has the following form. So, as I was mentioning before, each block will have the same dimension of the original Hilbert space. So each block is 2 by 2. It's 2 by 2. And we have an infinite number of blocks. Interestingly, it looks like this, Bz minus Bz. I always start with the 0 photon sector because it's in the middle of the road. So 0, 1. So this is BZ minus omega and BZ minus omega. And this is BZ plus omega, and this is minus BZ plus omega. There's not much question about it. It's the diagonal part of the Hamiltonian. So it comes from this matrix here, okay? Oh, yes, here, right? Thank you. Very good. And now I have to take these matrices and put them here and here and so on. Okay, here I will put the 0. It's very easy. Let's put 0 here and 0 here. Very nice. Now we have to put the matrices here and here. All right, you can convince, I mean, it's just a matter of putting them here. You're going to see that this is B parallel 0, 0, 0. B parallel 0, 0, 0. B parallel 0, 0, 0, 0, 0, 0, 0, 0. Okay? All right, this is minus 1, 0, and 1. Luckily, it turns out that this matrix that so Pedro was asking before, this is a hopping matrix. So it has these diagonal blocks, and it has things away from the diagonal. But luckily, we can decompose this into 2 by 2 blocks. So let me put more zeros here. 0 and 0 here as well. All right, but look, this thing here is a 2 by 2 block. This thing here is a 2 by 2 block. This thing here will be a 2 by 2 block. So there are a bunch of 2 by 2 blocks, and only that, okay? And only that. And 2 by 2 blocks we can solve. 2 by 2 blocks we can gladly solve. All right, so let's solve it. Okay, so what is the general form of this 2 by 2 block? This 2 by 2 block, so the 2 by 2 blocks have the form. All right, so they have the form of minus BZ plus omega L, B parallel, and BZ plus omega L plus omega. Like here would be L equals to 0, for example. Okay? And we can find the eigenvalues and eigenvectors of this matrix. I'm going to write as tau matrices here, matrices tau, because I don't want to use sigma again because these are not the same sigmas. I'll just decompose the way you can just find the eigenvalues and eigenvectors of this matrix. That's all. But I'll just decompose into Pauli matrices because it's easier to see the eigenvalues and eigenvectors. So it can be written in the following form: minus omega 2 times the identity plus B parallel sigma. Okay, let's try again. Omega 2 plus L omega times the identity plus omega by 2 sigma z minus BZ sigma z. Oh, sorry, I was going to use tau. Okay, tau z plus B parallel tau x, and that's it. That's it. Okay, this is the decomposition into Pauli matrices, and you can immediately find the eigenvalues of this matrix. They are given by epsilon plus minus L minus half omega plus or minus square root of omega by 2 minus BZ squared plus B parallel squared. Okay. Okay, very good. Right, so we have several blocks. All of them are 2 by 2. So if you look at them, they are not identical. So this block has minus omega and 0. This one has 0 and omega. This one has omega, and here it's going to be BZ plus 2 omega. Okay? So these blocks are 2 by 2 blocks, but they are not identical. So each block has a different value of L. Okay? So I'm solving all of them together. So this is, if I take this Hamiltonian and I plug L equals to minus 1, I get this. L equal to 0, I get this. L equal to 1, I get this. Okay? Okay, very good. So we can find these eigenvalues. And something that comes to mind immediately is that, well, you had two states. The spin can point up or down. But all of a sudden, you have infinite number of eigenstates. What is this eigenstate proliferation? It's not the same in crystals. In crystals, you have a periodic potential, but you have a continuous variable x. And then it becomes a continuous variable k. Okay. Here, it was not like that. Here, I had two states. And now, all of a sudden, I have a bunch of energies. I have infinite number of energies, infinite number of everything. Okay? All right. So I will address this point now. But 3, solve HF. And this will be the only time I'll be able to do this exactly. Okay? Only time. All right. So we solved for HF, and we found these energies here. But why do we have so many of them? And the reason is the reason that I said initially here. Okay? This proliferation is not proliferation of energies. It's proliferation of quasi-energies. So not all quasi-energies are physically distinct. And you can see that as you go from one L to the other L, you are shifting all of them by omega. You're shifting them by omega. And this is for free. You can do this for free. The same way as in a crystal, you can inject crystal momentum big G. So you can inject omega for free. So if we represent schematically what's going on, all right, if we represent schematically what's going on, we have two energies with a gap, delta, and the delta is 2 times that square root. So we have a delta that is 2 times the square root. And then we shift by omega, and then we repeat. And then we shift by omega, and then we repeat. And then we shift by omega, and then we repeat. Okay? But shifting by omega is for free. So this is called, I mean, if we fix one of them, let's fix this here. As usual, I'll fix the L equals to 0 case. Why not? I'll fix this here. You can call this the first Floquet zone. I'm not being very rigorous here because you can do this more rigorously because I'm mixing a bit. This L is not the same as this 0, 1, and so on, but that's not a problem. You can always, if you prefer to keep this guy and this guy, you're also fine. It's okay. All right? So this is the solution of the problem. You can see that the eigenstates are going to be overcomplete because we had the 2 by 2 problem, now we have infinite number of states. We have all these bases here as well. The question of how to find the unitary that evolves the system in time is something for later. Okay? All right, questions? Hmm?
What is the step number 4?
Okay, I'm making up the steps now, so let's think about step number 4. So step number 4 is we don't have this step number 4 here in this problem. Step number 3 was very successful. Typically, it will not be as successful. And step number 4 is not particularly present here, but it will be present in other problems. That is the following. Four. Okay. Uh-huh. These are the ones, yeah. These are the quasi-energies, yeah. Yeah, they are eigenvalues of this big Hamiltonian here. It's just that since it's block diagonal, it's more precisely I should be labeling like this, okay? These are all the quasi-energies. Step number 4 is choose the Floquet parameters that make the system interesting safely. Here we don't have this. The only what does this mean? The only parameters that I have here, what parameters do I have here? Okay, so I'm driving this with a magnetic field, and the magnetic field is rotating. What do I have? So in this case, for the spin half, I had the following parameters. I had a magnetic field that I'm calling, it has amplitude, it has an amplitude B parallel. And it has a frequency omega. Omega. These are the two new parameters. I didn't have these two parameters before. Here I have BZ, but now I have these two parameters, this and this. How do I make this problem as interesting as possible? Well, for the spin 1/2, there's not much that you can do. Okay? You get these energies, fine, that's okay. You can even drive it to resonance if you choose this equal to this. I mean, in principle, this is something that you can do. But that's basically it. It's not going to be like this when we try to probe interesting phases of matter. When we try to probe a spin system, I can choose state number 4 to produce, let's say, a spin liquid. When I drive a Kondo system, I can choose step number 4 to make it a two-channel Kondo lattice. Next lecture, I will take a trivial insulator and make it a topological insulator using 4. So the step number 4 has to do with what we initially called knobs. Knobs in Floquet engineering. And what do I mean by safely? Safely, there are some effects that you need to avoid because you want to have this plateau. If you choose, for example, a Hubbard model that is in the insulating limit, and you choose the Floquet engineering in such a way that you're going to be in resonance, and now all the charges can move around for free, it's not going to work because it will heat up. It will change the... If you're trying to find an effective spin model, it's not going to work, okay? Because the electrons can move around, and now they carry charge. So it's not going to work. So you have to do it safely. But what does it mean, number 4? What does it mean? It depends. It's extremely system dependent. All these steps are system dependent, but the other ones are more or less straightforward. Number 4, you have to think carefully, okay? And if 4 works, then you get the phase diagram that you wanted. That you had this tiny thing, now you have this big thing, okay? As a function of what? These things, for example, okay? As a function of field, as a function of frequency. Okay. I think I'm out of time, so we can start the next lecture by introducing something that is called a rotating frame that would solve this problem immediately, but won't solve other problems. It won't, but it will make life easier. And then we can start doing some perturbation theory because the spin half, the homework, one of the questions of the homework set is to solve the spin 1. analogous to the spin half. Right. 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 It comes from this word here, safely. If you, we're going to see this in more detail, but if you have an insulator, for example, that has some charge gap, and you drive it in a way that you are not, the charges are not moving that much. So you're driving it safely, the insulator safely. This is the best hope that you have that this plateau will live for long. For sure, if you choose this in a way that the charges can move around, this plateau will not exist. Okay, it will not exist. But the idea here is to avoid, we're going to come to this point later, avoid resonances. This is the first thing that you have to do, avoid resonances. Avoiding resonances is almost certainly necessary, but not necessarily sufficient. More questions? Well, for the spin 1/2 case, in which it's just a spin 1/2, I'm taking this from a spin 1/2 factory where it produces just a spin 1/2 and nothing more. This problem has only these levels. I can do whatever I want. But in real life, it's not like this. The spin 1/2 comes from someplace else. In particular, it may have charges degrees of freedom frozen, and then it. But here, okay. But to answer your question, this is not the resonant frequency. This is the frequency of the drive. The resonance would be omega by 2 equals BZ. Okay. Then it's a resonance. The resonance here is kind of, it will make the spin a little bit crazy, but it won't produce anything drastic. Oh, absolutely, absolutely, absolutely. This would be lecture 6. But yes, if you want to treat the time evolution or the effects a little bit beyond, if you want to, especially if you want to do, I would say something here. I don't know if Fernando is going to talk about this actually. Yeah, so okay, so it's before, yeah, he's going. Not much, yeah, but yeah, absolutely, the answer is yes. But again, if you have like a simple solid state problem in which you have non-interacting electrons and so on, fine, you can write down the Green's functions, but it's not going to be very life-changing. It's the same here. If the Floquet Hamiltonian works, it works. But the problem is if you want to add other things, if you want to connect this, if thing is going to heat up, maybe you want to connect this to a bosonic bath or some heat bath that can like dissipate a bit of energy and so on, and then Green's functions and all of these are extremely necessary. More questions? Okay. If we have what, a quench? Yeah, the quench physics is different. Then you don't, it's not periodic, it's going to be, you're going to drive the system out of equilibrium for some time and then the system will eventually relax. This technology is for the opposite limit in which you have something like oscillating uniform in time. But then with a quench, you would basically have to solve the problem from the beginning again with quench, okay? Yeah. Preferably, yes, yes, sure, absolutely. You don't want this this ramp to be very drastic because during this time you can produce a lot of things, right? So yes, you would like to do this as smoothly as possible. Yes, that's right. That's right. Okay, more questions? All right, let me finish by thanking once again the organizers for putting this mini course together. It's a great pleasure to be giving these lectures here. So today was lecture 1. We have 4 more, and very enthusiastic for the rest of the week. So let me thank José, Joe, and Rui for organizing this mini course, and I hope everybody enjoys it. Thank you.